We're now going to set up our dual color LED and write the script that will allow us to see both changes in frequency and changes in duty cycle. This will demonstrate how pulse width modulation can be utilized in order to dim an LED. As before, we will connect the LED black wire ground to the GPIO extension board ground. We'll also connect the yellow R pin wire to physical pin number 12, GPIO pin number 18. As mentioned previously, a good practice to do when using an online repository is to ensure that you have the most recent code. In order to do that, we'll navigate to ATTC 3260 in the terminal and issue the command git space pull. Depending on when you pull, it will show here whether there were changes or not. So now we have the most up-to-date code from the repository. I'll now open the File Explorer and navigate into ATTC 3260. Let's open up lab number 3.0 and the code 3.1.0 underscore pulse width modulation. Some of the code that we have written in this lab is similar to what we've seen before. First statement, import rpi.gpio, is our import statement for the library GPIO. Then we import time, which is the library that allows us to change time. Next we see a pin underscore R, and we assign that variable to pin number 12. That's physical pin number 12. The first line of code that is different from what we've previously written is another assignment of a variable. I'm calling this variable signal underscore frequency. This variable can be named anything. It could be banana, right? Banana equals 1. We're using a variable as a method to pass the signal frequency to any code or line of code that wants to call it. In this example, we're using signal frequency two other places within the code. I only have to change signal frequency at the top in the variable assignment, and that will then change the signal frequency value interpreted by the other two lines of code that use signal frequency. The next variable assignment is signal duty cycle. Similar to the signal frequency, anytime that I change signal duty cycle, any other occurrences of signal duty cycle variable in the code will also change. For right now, we're setting it to 50. Remember that duty cycle is the percentage of on time, so this duty cycle variable is 50. The next two lines of code we've seen before. The first one is setting the mode of the board. We will be using gpio.board, which makes it so that we have the physical location when referencing the pin numbers. The second GPIO setup is a assignment that pin R, which in our case is pin 12, is going to be assigned to be an output. The next line of code is a new line that we haven't written before, so let's spend some time identifying or defining each of the components of this line of code. First of all, the PWM underscore pin is simply just a variable name. I could name that anything I want. I could call it banana pin, right? I sure love using banana. So PWM underscore pin is simply just a variable name. What I'm setting that variable to is a GPIO dot PWM. That is a method within the GPIO library that allows me to pulse width modulate a signal from that pin. I set GPIO dot PWM with two separate parameters. The first parameter that I must pass to it is the pin number that I would like to pulse width modulate. In our case, we are passing it the variable pin underscore R, which has a value of 12. So pin 12 is being assigned to be a pulse width modulated digital signal. The second parameter that I need to pass to the GPIO.PWM method is the frequency. Here I'm passing it the variable signal frequency, which in this case has a value of 1. So I could have written this line as GPIO.PWM open parentheses 12 comma 1, but once again we're using variables to make this a little bit easier. So this is not turning on the LED. This is simply assigning the variable PWM underscore pin and giving it a value of a pulse width modulated pin. The next section of code has several print statements. These print statements will just allow us to be able to see in the console at what point in the code that we are. I've included two print statements to identify both duty cycle and frequency. This will allow us to ensure that we have properly set duty cycle and frequency because I'm giving it a variable rather than a fixed number. Next we will look at the two lines of code that actually turn on our number 12 pin, and that is a pulse width modulated pin. So our variable PWM underscore pin now has a method called start. The reason that it got the start method is because I assigned it to be a GPIO.PWM in the code above. So PWM underscore pin dot start starts the pulse width modulation. One of the pieces of information or parameters that I need to pass to the pin is the duty cycle. Here I am assigning the signal underscore duty underscore cycle variable, which we have placed at 50 to the pin PWM pin. So pin number 12 now is going to be a pulse width modulated pin that has a frequency of 1 and a duty cycle of 50. The line of code is contained within the while loop. Remember, anything that I indent after the while loop will remain in there. In this particular while loop, we are just saying while true. True will always evaluate to true, so this code will just continue to run until we close it or stop the code by pressing Ctrl+C. The final two pieces of code are simply to print that the program has ended and the final cleanup of the GPIO. Navigate back to the terminal, and you will, if you're not already there, navigate to the ATTC 3260 folder, and we will be working within lab 3.0. If I do an ls, the lab that I will be running is 3.1.0. So I will now issue the command python 3.1, and then I should be able to push tab. When I press the enter key, I should see that depending on how I ran the code previously, you may get this runtime warning, but it's simply a warning and it should run okay. So the first print statement indicates that we have started the program. Then I say that the duty cycle is, and remember we were just calling or asking for the variable. So the duty cycle that we're calling for is duty cycle 50, and the frequency that we're currently utilizing is frequency of 1, which would translate to 1 hertz or 1 cycle per second. And then I see the print statement that says the LED is on, and that should indicate that I am ready to run. Here we can see the LED is blinking. Your LED should be blinking at a frequency of 1, meaning 1 cycle per second. So you should see it go off and then on in a 1 second period of time. A half a second it is off, and a half a second it is on. The duty cycle for this is 50%, meaning that half of the cycle the signal is in the on position. We will now be making some measurements with the multimeter. You may or may not have to move over your GPIO extension board in order to expose at least one more pin. That extra pin is where we'll be connecting the multimeter. We'll take our black multimeter lead. Notice that I have this fluke extension on there that just makes it a little easier for me to push down into the breakout board. I'm going to push it into the breakout board at the ground pin, so it should be matching right against the physical pin number 20. My red meter lead will be placed in the physical pin 12, GPIO pin 18. Rotate the dial of the multimeter to volts DC. We can see that the range of the volts is changing from somewhere around 0 to 3.1. In order to get a more accurate measurement of the voltage that we are seeing, we are going to use the min-max button. If you press the min-max button, you'll see some beeping that will occur when it gets a new value for min and a new value for max. If I press the button again, I will now get the maximum voltage that the meter will read. If I press it one more time, that will give me the minimum voltage. Here we see it. And then I press it one more time and I get the average voltage. So we can see here that we're getting about 1.56 volts on average. Next, I'm just going to rotate my dial away and then back to the volts DC. And then the button on the right is for frequency and duty cycle. If I press it once, I get a 1.00 Hertz frequency. If I press it the second time, it will give me my duty cycle. We set both the duty cycle and the frequency in our Python script. We set the frequency to 1 Hertz and the duty cycle to 50. The results are we see the LED blinking. Here's a screenshot of the 3 values that I measured on my breakout board. Yours might be slightly different than this. I got a maximum voltage of 3.118 volts DC. The minimum voltage was 0 volts, and the average voltage was 1.548. On a previous video, we discussed that a pulse width modulated digital signal with a 1 Hertz frequency and a 50% duty cycle would essentially divide the high voltage in half. And we see this exact behavior in our multimeters as we measured it. We went from 3.118 and divided that by half, and we got the value 1.548. Because the frequency is so low, we can actually measure this on a multimeter. As we increase the frequency, it becomes more challenging to measure both the minimum and the maximum, and we will demonstrate that in future videos. Next, we're going to do the same script, but we're going to measure it with an oscilloscope.